this is article 2, right? And this was already pretty impressive. And then he went on to the next thing. So the previous one was, I think, April, so this is June, right? We started in March, so this is a pretty intense year. And so it's called On the Electrodynamics of Moving Bodies. Well, okay, so the thing is, he describes how space-time, so the 3 space coordinates and the time coordinate, are influenced by the speed of, well, something. And that is, of course, what we later now call the special theory of relativity. And classical is basically Newton, where he says, well, you can add velocities. So if I'm on a train moving forward and I throw a ball forward, the ball has the velocity of the train plus what I add. And if I throw it backwards, then I have to subtract the velocities. So if this train is moving forward and it shines a light forward, then of course the speed of light is basically the speed of the train plus the speed of the light from the lamp. And if I shine backwards, then you have to subtract. Well, yes, but no. It doesn't work like that. But classically they thought it worked like that. And because light was, well, it was described with waves and pretty good, and it worked, they assumed it had to have a medium in which to do this wave motion, basically. Like water, waves need water, like sound needs a gas. And basically light needed an ether, not the chemical stuff ether, but an ether, some medium that basically carried the waves. And of course, absolute space and time, that means you can add velocities and basically lengths stay the same and everything, nothing changes. That's Newtonian. And well, Einstein said, well, space and time are relative, not everything. If you say, well, Einstein said everything is relative, that's definitely not true. He said space and time are relative. And the ether is not needed. So basically, if it's not needed, that's Occam's razor for you, then you just discard it, right? Don't get all this extra stuff if you don't need it. So basically, away with this. Because if you travel in this ether and you travel against the waves, then you measure a different velocity than if you travel with the waves, right? Well, with sound, you see something happening like that, but with light, we always measure the same speed. So, what he basically said is, well, they wanted to solve this paradox, this thing. Newton, more than 200 years, he described motions perfectly, and we still use Newton to send satellites to planets, and it works fine. But electromagnetic radiation, and in the laws of Maxwell, in the Maxwell equations, there is a constant which you can definitely interpret as the light, the maximum speed of light, and this c, this constant. And basically, for light, they had experiments that showed that you couldn't add the velocities. Basically, however you move, doesn't matter. When you measure the velocity of light, it's always the same thing. So if the train is coming towards you, shining a light, or traveling away from you, shining a light at you, doesn't matter. And that's very strange. So he started with 2 assumptions, and he used an inertial reference frame, basically moving at constant velocity. If you accelerate, it's much more difficult. It took him 10 years to describe that, so next time, perhaps, I don't know. But in an inertial reference frame, he just made 2 assumptions. Pretty simple assumptions. Well, one, that's very nice. The laws of physics are the same everywhere in an inertial reference frame. Okay, so that's good. That's not very special. But the other thing is, the velocity of light is constant. Doesn't matter it's independent on the source, the velocity of the source. So if this train is coming towards you or away from you, it doesn't matter. You always measure the same velocity of light, which is very strange. So that leads to shocking conclusions. And this has been known for more than 100 years, and probably some of you will be shocked. Anyway, so let's go on. He was not an experimenter. Every time you see this drawing of Einstein with a white coat and test tubes, that's ridiculous. He never did that. He was a thinker. He never went into a lab, I think. He was basically denied a job in a lab because he wasn't prepared for that. He was thinking about stuff. One of the things he did was invent thought experiments. And one is the light clock. So in a light clock, you have a light source, and it sends a light beam upwards, and there's a mirror, and say that this mirror can detect when the light is hitting it. Then you have a clock, basically. So you need to take some time. something like that. You have a light clock. So if you travel with this light clock, then of course you can measure the time it takes this light to travel from the bottom upwards, right? If you are traveling with that clock and I'm watching you, I can see that light beam. Basically, you see the light beam going up and down, but I see the light beam going like this because you're traveling forward, where at the same time the light is traveling up. So I see the light basically traveling in a longer path. So if I measure the light velocity, I see this longer path. I know, well, I measure the light velocity, so I can determine what that takes more time. Because you travel more distance, you need more time with the same velocity of light. So we need Pythagoras and some magic. So Pythagoras is easy, right? This one, everybody knows this, right? And this distance traveled by the light is longer. This is what you see when you stand to the side. So it takes more time if I'm watching the light where you're traveling with it. Well, and then from the magic appears the time that I measure along the side is some factor times your time you're traveling with the light and the train. And this is the factor, and that's the v of the train. This is the velocity of the train, and the c is the light speed. So this is some factor. We'll do a calculation. And basically for lengths, something similar happens. So lengths that I measure are different from the lengths that you measure. Also by this factor, well, 1 over gamma. It's called the Lorentz factor. Lorentz was a physics professor in Leiden, and Einstein looked up to him. So that tells you something. And basically, this factor was already thought of before, but he applied it here. And if you want to know what's behind the magic, then you can still watch. But if you're afraid of a bit of math, then close your eyes now. But anyway, this is it. So basically, you use Pythagoras, and it's not that hard to derive. Okay, so you can trust that. Okay, read it later on, perhaps. I don't know. So let's see what this means. Okay, so I thought this was going to go important, but anyway. So we have the formulas up here, right? So that means that clocks that move tick slower. Because you say, my clock takes 1 second to go up and down, for instance. But I see that it takes more distance, so more time. So I say, yeah, well, your clock takes 1 second, but I'm counting 3 seconds here, mate. So it takes more time. So basically, your clock is running slow. Also, lengths are different. So you say, oh, this thing is 1 meter long, and I say, no, it's only 60 centimeters, something like that. And that's very strange. So in a rocket, yeah, and you already see the answer. Sorry about that. Was supposed to be a surprise. Anyway, if you travel for 10 years with 80% of light speed, straightforward thing, you travel 8 light years. No surprise there. The gamma factor, by the way, if you travel 80%, which we can't, not because physics doesn't allow it, but because our technique doesn't allow it yet. But this is very high speed. But basically the gamma factor is this number. And that means on board, you have your time t, and I measure t prime. So I measure 10 years going by. So on Earth, we're staying behind, we're measuring, oh, the rocket is going for 10 years. But on board, your clock is only running for 6 years. So you're only 6 years older. It's not just the clocks, every biological process, time itself is running slow. So it only takes 6 years on board. The thing is, I can see you've traveled for 8 light years. So if that astronaut has traveled for 8 light years and sees on his clock, wow, I've spent 6 years in space, then he would assume that he traveled with a higher speed higher than the velocity of light. But it doesn't, because he only sees that he has traveled 4.8 light years. And now, of course, we haven't done this experiment because we can't travel these speeds. But we can look at subatomic particles and we can detect them, and they move at really high speeds, close to the velocity of light, and they show this effect. We can measure that, right? So it really works. And another thing.
Sorry, can I ask you a question?
Sure, yeah, of course.
You said that these subatomic particles, they travel almost at the speed of light.
Yes.
Does that mean that it's not the speed of light? So this different timing is at the speed of light, but also less than that.
Yeah, definitely at 80%. Basically,
80%.
we take roughly 10% of the speed of light. You start to see effects. Then the gamma factor is really well, adding like a percent to length, or subtracting a percent from length and adding a percent to the time. So from about 10% of light speed, it really starts to work. But these subatomic particles, like muons in the atmosphere, that are basically the Earth is bombarded by radiation from outer space, or basically protons. They bump into the atmosphere and they produce muons. These muons, they have speeds like more than 99% of the light speed, so almost at light speed. And they have a really large gamma factor, and that basically means that they live, muons, if we see them in the lab, they live for 2 microseconds roughly. In the 2 microseconds with light speed, you can travel 600 meters. They originate from 10 kilometers height, and we measure them here. So how can they travel 10 kilometers if they only live for 600 meters? Well, because their clocks run slow. So they can live 2 microseconds in their time frame. But if their clock runs slow, then they can travel for a longer time in our time frame. And the other way around, they don't think they're traveling 10 kilometers. They see the Earth much closer. So they see that, yes. So told you, it's very strange. So a muon sees it very differently. Well, not just muon, everything that travels really fast sees lengths shortened, and we see their clocks moving, well, running slower. Another thing is that simultaneity, so things being at the same time, is also relative. That means there's a nice thing called the ladder paradox, where you have, it's always with a farmer and his help. And of course the farmer is just standing still looking at the help. The help is running at almost light speed with a ladder. And the ladder is, in the rest frame, is basically, well, with the help, is too long to fit in a barn. But the thing is, if you see this help running, then basically the ladder is shorter and it can fit in the barn. But the help is running towards a barn that is shortened and can't fit in the barn. So the farmer is able to shut the doors while the ladder is inside at the same time, so the ladder is completely inside the barn, whereas the help says that can never work because the barn is too short. So what happens to the doors is basically, he goes in, the front door closes, then has to open, and then the back door closes. So the doors are not closed at the same time for the running help, but they are for the farmer. So there you go, time is relative. Right, so that's very strange. That's in short, that's the ladder paradox, so you can look it up. It's a very famous one. So it's a paradox is of course something that's a contradiction, but not really. It is actually happening, but it basically assumes that, and this is also of course against Newton. This was a controversial thing. English physics was all about Newton, so they didn't like that. And this was some German scientist, and well, they were never big friends, Germany and England. So